Okay, so it's a pleasure to be here. Thank you again for all the organizers. I feel some continuity from 2018 at Rice. So it's great to in Houston. So it's great to have this again and to be here. So I'm going to talk today. I was actually originally going to speak about the Minimax Wiener sequential testing problem that was recently published in SciComm, but because people were speaking about the spider, I wanted to talk about the Dubins spider instead and a variant. And the talk that I'm going to give today sort of touches, I can't go into any one paper too deeply, but I can sort of go into the three papers in blue somewhat well, giving you a high-level analysis. And even though Larry's name, to continue from 2018, isn't on any of these papers, at least three of them were directly motivated by him, I should say. So that does connect the past to the present. So this talk today is going to be about the Brownian spider. We know about it from Pablo's talk, but again, also known as Walsh-Brownian motion, as first introduced in the epilogue of Walsh. Early constructions were given by Rogers using resolvents. We won't be utilizing resolvents today, unlike the last talk, by Baxter and Chacon using infinitesimal generators, by Salisbury with excursion theory, and by Barlow, Pittman, and Muir as a process on n half-lines or ribs, meaning in a common point O, where that point O is usually the origin. Doesn't need to be, but it usually is the origin. And we're going to work with the last four of these constructions in the present work. So following the last four of the constructions we considered, Barlow, Pittman, and Muir, a Brownian motion on a spider, how do you construct it? You construct it from a standard reflecting Brownian motion. You take the absolute value of WT, where WT is a standard Wiener process, by assigning an integer amongst the n ribs, I equals 1 to n, uniformly and independently to each excursion. It need not be that in general, but in the classical case, it is independent and uniform. You can consider sort of, spokes on a wheel where they might not be equal angular, and you might have different probabilities, but no, in this case, we're going to assume they're all uniform and independent. And from this definition, it follows that for the case n equals 1, you're dealing with reflected Brownian motion. For n equals 2, you're corresponding to standard Brownian motion, because you're going to be looking at, when you have the process, the sup minus the n for the running Brownian motion. So in case it wasn't clear from before, this is a sample path realization for n equals 3. This is when you would have 3 rays. This is the first non-trivial case, right after you have reflecting Brownian motion and standard Brownian motion. You have the 3 spider, as it would be called. And here, Wi is a Wiener process, and Si is the running maximum on each of the ribs. Okay. So now in more detail, returning to Barlow, how do we realize the Brownian spider? What's called ZT. It can be realized as a bivariate process. The first coordinate is the absolute value of WT, reflected Brownian motion, and RT is the rib on which the process is located at time t. You can decompose the reflected Brownian motion into excursions away from 0 with endpoints, such that the Wiener process evaluated those endpoints and the absolute value is 0. The notation RT equals I is used to note that the excursion will occur on rib I. And an important quantity that we'll be using throughout was in the previous slide is the supremum of reflected Brownian motion on rib I. So SIT will be the sup corresponding to the ith rib of the reflected Brownian motion. And of course, SIT will be strictly positive for all I and for every t greater than 0 if the initial point is 0. That's a Brownian spider. The Dubins spider. it is a Brownian spider, but it's a specific question. Okay. The Brownian spider doesn't have a specific question. It's a construct that started with the 4 papers, and we invoked the Walsh-Brownian motion from Pittman, from Barlow, Pittman, and Ure, right, in order to construct the bivariate processor we'll need. But it doesn't answer any specific question. The Dubins spider problem attempts to answer a specific question. So in an attempt to understand the unboundedness of the variation of the Wiener process, and this is from Itzhak Melechson from University of Tel Aviv, some probabilists among the late Lester Dubins, David Gilad, Itzhak Melechson, and the late Larry Shep went into a different direction of search. They wish to find a stopping time to maximize the coverage of Brownian motion on a spider for an expected time. Colloquially, this became known as the Dubins spider problem. And what do they mean by coverage? They wanted to calculate Cn in equation 2. Cn are called the spider constants. So you take the soup over all stopping times where you normalize them to 1, right? So that you're dealing with the same time frame of the expected value of S1 tau up to Sn tau, right? That is the definition of the coverage of the spider. And by simple scaling argument, you can show that an equivalent formulation would be in 3, right? Where you just take the expected value of the sum of the supremums. It's bounded by the spider constants times the square root of the expected value of tau. And calculating the spider constant Cn for all n became known as the Dubins spider problem. So the Dubins spider problem is a specific question about the Brownian spider in terms of measuring the coverage of the Brownian spider precisely as follows. But when I first looked at this work, of course, I realized that without them saying it, the spider constants C1 and C2 had been calculated years before. So C1, again, corresponds, C1 corresponds to having 1 ray, C2 corresponds to having 2 rays. They end up being root 1 and root 2. Why were they calculated before? Under a different guise, Dubins and Schwartz asked the following questions about mean 0 Cadillac martingales bounded in L2 with variance sigma squared. They asked what's a maximal possible value of the expected value of the running max of MS for the Cadillac martingale, L2, bounded in L2. And what's a maximum possible value for the expected value of the running maximum of the absolute value of MS? And they proved that the expected value is at most sigma root 1, and the expected maximal value, absolute value, is at most sigma root 2. Yes. Okay. And indeed, the question was then asked again by Dubins, Gilad, and Melchson about the maximal value of the expected diameter. And here the diameter is interpreted in the natural way as the expected value of the max, the running max of the martingale minus the min, which was proven to be sigma root 3. All of the inequalities are also proven to be sharp. So they do correspond to the best constants. Right? And then, of course, the corresponding best worst cases for martingales, you can realize them as stopped standard Brownian motion. Why? Because optional sampling, right? The properties of the generalized martingale inequalities generalize the stopping theory through optional sampling. And so, of course, this has led to questions concerning martingale inequalities to often be reinterpreted as optimal stopping problems for standard Brownian motion. So when I came across the problem, I saw that nothing had been done for 3 or beyond. Now it's completely open. So the spider constant Cn for 3 and beyond were not known. And I don't mean to disappoint you, but they're still not known. But in a variant that I did recently, they are all known. So there's some good news and bad news. Or I should say, given that this is one of the hardest problems, it's not so surprising that there would be some bad news. And I think you'll see in a second why it's so hard when you get to 3. So in using dynamic programming approaches, sort of how I would think about optimal stopping problems, I would say for the longest time until I met Goran, I would only think about it in terms of dynamic programming problems. And you can follow 2 methods. You can guess a candidate, calculate the reward function, prove its excessiveness, or you can guess a reward function and establish optimality by proving excessiveness. Dubins and Melkson and Gilad employed the first, and in my 2 papers, I'm going to employ the second. Of course, I just want to emphasize before going further that you only have the candidate, right? These approaches only give you the candidate for the reward function. Doesn't give you any rigorous proof. After that, you need to check the excessiveness and optimality of the constructed function. And if both excessiveness and optimality hold, then the candidate coincides with the value function and the optimal stopping problem is solved. So here will be the notation that we'll work with in formulating the value function in the dynamic programming context for the Brownian spider. So we'll let R be the index of the starting rib, X be a fixed distance along the rib R, C and M be finite constants, and we're going to let S1 to Sn be the distances that have been covered on each of the respective ribs. These are going to be the key coordinates because they represent what has been covered in the state space that you're working with. And so when we consider 3, we'll look at S1, S2, S3 as a state space. Right, like this. And so for every value of C and for every R and X, we're going to write this value function. The value function is as before. We take X, right, the fixed distance along the rib R. The distance is covered, S1 to Sn. This value is C. We're going to simplify it to be a half later on so we don't have to deal with it in general. It's just going to be the sup over the expected value of tau bounded by some M of the expected value as before. And so before we start doing this, it's important to emphasize that we not only need to calculate this value function for 0, for x equals 0, and for all S1 to Sn being 0, but also for every point on the spider at rib X and every rib R as an initial point, and for every starting position. And that's because standard methods of martingale for stopping problems really don't work, at least if you're looking at the Dubins, Shep, and Chiryaev context, unless you find the formula for the value function for every starting position. So now we're going to proceed with dynamic programming and guess the value function. This is going to be relatively straightforward. So again, we're going to guess the value function, right? And then prove that indeed it is the optimal value function. So we can guess the properties, right? The properties are fairly elementary. We're going to assume that the value function will not depend upon the rib. We have a uniform and equal probability on each rib. So if it depended upon the rib, it wouldn't be the right construct. The second is a Kirchhoff condition, right? In dynamic programming and networks, what does a Kirchhoff condition say? It says that you take the sum of the derivatives of the value functions, and that has to equal to 0, right? This is well known in dynamic programming and networks. The third is normal reflection, right? You take the derivative with respect to the coordinate of the value function, and that equals 0 for all R. And this is, of course, in Goran's paper From Brown to Feller and Beyond. You can see many examples of this. D is a super martingale condition. the 1/2, of course, comes from the infinitesimal generator. E is just true for any optimal stopping problem, the value being greater than the gain. And then you note that if strict inequality holds in E, you'll have the super martingale become a martingale in the continuation set. So properties A to F are the properties that we guess the value function will have. We should also define the stopping set. So intuitively, the stopping point, you'll be far away from a boundary point. That is where SI would increase. And thus, you'll accept the reward V hat to be the sum of the coverage, S1 to Sn. And you'll identify the stopping set to be when the value function gives S1 to Sn, the sum of S1 to Sn. Now, this doesn't say what the stopping set should look like. It just says, well, if a point S1, S2, S3 is a stopping point, then the value function at that stopping point will give you this. It doesn't say anything more. So how do you prove the optimality of this guess? Well, first you start with the inequality that V hat will be bounded by V. You consider a continuous local supermartingale, YT, which is V hat. ZT again is a bivariate Brownian spider. ST is this vector of the supremums on each of the ribs. And C again is this constant that we're going to set to 1/2 later. Now we can invoke the properties. By A and B, Y will be a continuous local supermartingale at x equals 0. It will also be a continuous local supermartingale at x equals SR by property C. And it will also be a continuous local supermartingale at any x by property D. And for a bounded stopping time tau, it follows from Dubs' optional sampling theorem that the following holds. And therefore, property E, right? Again, property, just to go back, property D was a super martingale condition. This is just true for any optimal stopping problem trivially. Okay, so property E will give us that for any bounded stopping time, this holds. And so we have the inequality in this direction. To prove it in the other direction, well, you know that by the last property, F, when the super martingale becomes a martingale in the continuation set, that it will hold for the right tau, which is the particular stopping time that's approximated by uniformly bounded stopping times. In our setting, it exists. It's the first entry time of the markup process, ZS. Z again is the Brownian spider, right? S is a vector of the supremums in the set where the equality holds in property E. And when property F holds and when equality holds in D, Y will be a local martingale up to the first entry time. You then invoke Dubs' stopping theorem and the reverse inequality holds. Okay, so now that you've proven you have the right candidate, you'd like to use it to find the spider constants, ideally. An easy claim is that AN, given as such, so AN, X is the origin, you have R, you have 0 to be S1 to Sn, and C, that's equal to theta n over C. Theta n is completely independent of C. And the proof is trivial. V has to be of this form because by the scaling argument, you can reduce the problem to any given value of C, and that's because you can show 10. And so if you start then at the starting point, and S1, this is a typo, it should have Sn, is 0, then you'll obtain the above form for AN. So going a little bit further, Again, you define the supremum for any C and for any tau. You'll have the following inequality. You let M be the expected value of tau. You can minimize over C, and you get the following inequality. You want to know where the infimum is attained. Simple optimization problem. It's obtained at C equals root theta n over M. It gives this bound for any n. So Cn is 2 root n for any n. And that shows you that, of course, you only need to find V for one value of C. And so we're going to take C to be 1/2. And because you can employ the general equation before, tend to return to the general case without any difficulty. So what's a corollary of this? Well, a corollary of this is that you can get the spider constants, but in a quite different way. So for n equals 1, you guess the function v hat of this form. And you can show that when x and s are between 1 over 2c, that all the properties a to f are satisfied. And when x is between s and s is 1 over 2c, this function satisfies indeed all the properties a to f. You get theta 1 is 1/2 and c1 is root 2. And the second corollary is that you can do the same thing with n equals 2. You write, you can simplify this equation as follows with these constraints. And again, just straightforward arithmetic, you arrive at the spider constant. Okay, so then the question is, how do we extend it to beyond 3? So in order to find theta 3, which will give the spider constant, right, if we can, for 3, we need to extend the calculation of the value function to smaller and smaller values of the s's and eventually to s to be equal to 0. And notice that we do have a vector of 5 coordinates, right? But we're going to look at points in the state space, and the coordinates s1, s2, s3 here are the only key coordinates among the 5 coordinates that we need. And so the first region we'll consider in case 1 is when all of the s's are greater than or equal to 1. Again, that won't include the origin, so we won't be able to find theta 3 from that. The reason we start there is that we long conjectured, and indeed we can now prove, that S1, S2, S3, this element of the state space, is a stopping point if and only if SR is greater than or equal to 1 for all R. So you will have a stopping point if S1, S2, and S3 are all greater than or equal to 1. If 2 out of the 3 are, but the third one isn't, you don't know if you have a stopping point. It only gives you one characterization of a stopping point. So that's the first region. You guess the value function in this first region. You can check that it satisfies the properties. It's straightforward to check that it has the properties A to F. You introduce this local super martingale and a local martingale where the 5-dimensional process is in the continuation set. By the theory of the optimality of reward function, all I mean is the theorem that said v hat was actually equal to v. You can conclude that yt is a local martingale here and a local super martingale here. And it therefore follows that in case 1, you've identified the optimal value function. The guess is the optimal value function. Of course, you're unable to calculate theta 3 yet because the region for case 1 doesn't include the point O at the origin. So what do you do then? Consider a second case. So now we're going to consider where not all of them are greater than or equal to 1. We're going to consider a case where S2 and S3 are greater than or equal to 1. S1 will be less than 1. And how much S2 and S3 are greater than 1 will depend upon some function where you can determine there needs to be continuity at this common boundary. And the rationale behind this is that you're looking for when to stop. In the first case, you have a stopping point if S1, S2, and S3, yeah, 5 minutes, okay, are all greater than or equal to 1. In this case, you're looking for a possible extension where you have S2 and S3 are much greater than 1. So it might be optimal to stop even if S1 is between 0 and 1. It might be, heuristically. It might not be. We don't know that. But that's a heuristic. And for r equals 1, in this case, you can write the value function. For r equals 2 and 3, you can also write the value function. And you can actually give the beta, in order for the value function to be satisfied, implicitly as the root here. So that's actually a pretty nice achievement, that you can actually get this beta. I'm sorry, that you can actually get this beta analytically in 17. Again, we're not yet there yet. We can't provide an expression for theta 3 because we don't know V at O. Okay, so we go further. Case 3. Case 3 is even more complicated. So we take S1 to be less than 1. Now we consider the fact where S1 and S2, S1 is less than 1, S1 is bounded by S2, which is bounded by 1 plus beta S1. And S3 is going to be bounded below by another function, 1 plus b. So you're trying to determine from case 2, you have S1 less than or equal to 1, and you're looking for possible extensions of how large the S's might be on the other ribs so that it's optimal to stop, or that you have a stopping point. It's considerably more difficult than case 2. You can't solve for the boundary analogous to beta, but you can succeed in finding a nonlinear integral equation for B. That's a nonlinear integral equation, and it also uniquely determines B. We proved that. So in order now to calculate theta 3, we have to calculate V at O. In the logical progression between these cases, we wanted to extend the calculation to smaller values of S's and eventually to S0. And what keeps us from succeeding? We can't directly express B here. So we can express beta, but we can't, as hard as we try, we can't actually find a representation for the function B. And that actually prevents us from going forwards. But it does explain why the 3 problem is much more complicated than the 2, because you have all these state spaces and you have to solve for these functions analytically, and it's terribly complex to do it. So what did we do after that? Well, so I want to end on a more positive note. Okay, so this paper was still published because it gives something new, but not a slam dunk paper. What do you do when you have an impossible problem? You make an easier problem. And the easier version of the Dubins Spider problem is the following. Instead of keeping track of the n arms, keep track of the 2 longest arms. If you run into so much problem with having 3 in this state space, surely that if you keep track of the 2 longest arms, you will not run into the problem that we ran into before. And so in 2024, we considered a reformulation of the Dubins Spider problem, where the task becomes to calculate Cn for all n in this inequality, where dt corresponds to the true diameter of the spider process. And the diameter corresponds to the 2 rays at a time that are longest. So for example, in this picture with 5 rays, the bold segments indicate the points visited up to time t. The longest rib is R5 here, the second longest is R3. Those would be the only ribs included in this calculation of d tau. This paper is terribly complex, and which is why I didn't just speak about it alone. I tried to speak in 25, 30 minutes before, and it was completely inaccessible. But I just want to tell you the general strategy and then I'll end. You use the time homogeneity argument to find the optimal constant kappa n in this inequality. By scaling properties of Brownian motion, this S tilde will also be a spider process for any integrable stopping time. And you can obtain an expression for the expected value of d tau as follows, using the optimal constant kappa n. You then optimize over lambda, you obtain this inequality. To see that the constant is optimal, you have to construct an integrable stopping time. And then the estimate in 21 from here will eventually give rise to this optimal stopping problem, which is a supremum taking overall stopping times tau of s. It turns out that the corresponding value u extends to the value function on the entire state space. So that is a positive result. In the end, the punchline is that Cn for all n converges to approximately a value greater than root 3. So it converges to approximately this. And the tempting conjecture right about the spider was that for C1, you had the constant to be root 2. For C2, you had it to be root 3. It would be tempting to say that that C3 is root 4 or 2. I don't think it is from simulation alone, but it could be. But this Cn doesn't answer the same question, of course. It just says if you keep the longest two ribs, would the spider constants converge? And indeed they do. So here are some references. Again, the initial work, the paper that actually solves the reformulation, this 2016 paper, this 2025 paper. Thank you.